Astrobiology colloquium. This is the last one this quarter, almost at the end of the academic year. So today I'm pleased to welcome Jacob Buffo from Dartmouth, where he's a research scientist. Was a postdoc until recently, but then he got a couple of big grants and they gave him a salary increase and a different title. So he works on ices and brines, and particularly how they relate to icy moons in the outer solar system, and also analog environments on the Earth. And he did his PhD at Georgia Tech, 2019, I want to say, yeah, where he worked with Brittany Schmidt, and he's doing lots of interesting work, including some work on lakes in British Columbia, which overlaps a little bit, or so it's different with some work that we're doing here. So that's why I invited him, because I thought what he has to say will be of interest to many of us. So take it away.
All right, thank you so much for having me. Yeah, so I thought today I'd kind of talk about a spectrum of things that I've been working on. One, some of the field work that we've been doing up at British Columbia, as well as some modeling work that I've been doing over the past few years to kind of see if we can model these ice-brine systems, and then try and convince you that these are some really unique and interesting analogs for planetary ice-brine systems. Feel free to stop me or ask questions at any time. I know this is like a diverse and general talk, so if you have any questions, go ahead and ask. So first, I thought we'd kind of zoom through some of these solar system environments that we're talking about, these ice-brine systems. So here's kind of a big spectrum. What we're looking at, and some of our favorite moons and different things like that, that can potentially house these systems. So one of the things that we need is we need to be beyond the frost line, which is basically far enough out in the solar system that we can have ice on the surface, which basically means that everything from the Earth beyond is going to be some prime environments to potentially house these ice-brine systems. So starting with Mars, both in the past and in the present. In the past, there was probably enough liquid to potentially have both lacustrine and potentially ocean environments, and that these environments were probably very salty, just like our own ocean. And so because it probably also had cold surface temperatures, there's a good case that we probably had ice-brine systems, both things like lake ice, as well as basically what we would have here as sea ice on Mars. In the present, there's also a lot of ground ice. This top image is basically an area at the Phoenix rover site where they dug through and just saw shallow ice. And we also have large polar caps on Mars as well. So the idea is that even on present day Mars, there's probably a good chance that you're going to have this subsurface brine reservoir at depth that's probably still interacting with a cryosphere. So you're going to have ice-brine environments there as well. Ceres, biggest asteroid in the asteroid belt, probably has this kind of icy outer core, and it potentially has this residual brine layer at depth. Probably had a big brine layer at depth, at least at one point in its history. And also where you get impactors, like the bright spot here, the idea is that if you have this impactor come in and you melt this kind of icy outer crust, you can basically create a big brine chamber that will then eventually freeze out and overpressure. And that's basically what we see at these bright spots. These are salts that you can actually see on the surface. So there's a good evidence that potentially at present and both historically, Ceres probably also had ice-brine environments as well. Then we think about ocean worlds, moons like Europa and Enceladus, where you have kind of like this icy shell, this ice one layer, and then a subsurface ocean beneath that. And then kind of a basal seafloor, kind of like this picture on the left. And in this system, these ice shelves can be very active. We see a lot of geology on the surface. They're kind of reworked in young surfaces. So our idea is that they're probably having these kind of like ice geophysical processes, and that you might have different brines and different hydrological environments moving up through the ice shell and throughout the ice shell. And then Enceladus on the right, you basically have a system at the South Pole where the ice is thin enough, and you open up these fractures, and there's actually evidence for these plumes of brine getting kind of sprayed up, and they were actually measured by Cassini when they flew through. So one more piece of evidence for briny systems. And then we get into some more exotic systems farther out and then bigger planets. So some of the larger Galilean satellites like Ganymede and Callisto can actually have thick enough hydrospheres and cryospheres that they might have this ice one layer on the outside. So ice, what we think about, then a global ocean, and then potentially high pressure ices at depth. So if you get deep enough in the ocean, you can actually get different phases of ice that are more dense than water and things like that. In Titan, you might also have ice interacting with hydrocarbon systems. So the surface is cold enough to have things like methane and ethane in liquid phase on the surface. So that's not exactly brine that we think about in our ocean as like a salty system, but you might have different hydrocarbons and different impurities in these systems that are freezing and interacting with these ices. Triton is a moon of Neptune, and there might be ammonia in that ocean. So that's kind of another impurity. So brine in this is in kind of when I think about it can basically be anything that has solution impurities in it. And then the one that we probably know the best locally, we have sea ice that forms in the North Pole and the South Pole seasonally, which is basically when the ocean freezes out. And these are some images of the bottom interface. So you can see they're very kind of like structurally dynamic and porous. So you can see all these like frazzle crystals at the base of sea ice on the left and kind of this very mottled surface at the bottom. And then when you start zooming in on the right, you basically see that there are these kind of porous environments that are very well habitated in our sea ice on Earth. So this top right picture is just a layer of algae that lives in this bottom layer of sea ice. And if you keep zooming in, you can see these pores that actually form. These images in the middle are actually brine channels and pores in the sea ice, which is basically where these things live. So the idea for this is basically, you have this thick layer of ice. At the bottom of this layer, you have this porous system that's basically inhabited by these microorganisms. That's kind of this biological layer at the base here. So when we zoom in, what we're basically getting is when we start to freeze out the ocean, the brine gets rejected into these pore spaces. And so you have these high salinity brine channels, which is a micro CT of sea ice here, where the brine channels are in the white here and the negative space is actually ice. When you keep zooming into these systems, you can see that there's like networks and veins of brine in between these individual ice crystals. And you can actually image biology in these systems. So they're very dense, they're very rich systems, and it's really the primary producers for these polar oceans. Beneath ice shelves as well. So these are images beneath the Ross Ice Shelf and the Thwaites Glacier, where basically anemones and other things basically live at this interface and burrow up into the ice and kind of take advantage of this interface between the ice and the ocean. And this is actually at the grounding zone. So this is like hundreds of meters back from the open ocean on the right-hand side. And things are really just thriving, but they really take advantage of this interface and utilize this as kind of a place to live. And then life in lake ice. So this is actually a chunk of ice from some of the lakes that I'm going to be talking about, where basically you can see just from the color even, that there's this pretty significant gradient where on the right-hand or on the left-hand side, which is the bottom of the ice, it's a lot greener and there's a lot more biology than there is on the right side. And we can see that in the fluorescent microscopy images on the right, where basically as you go down in the ice, even though there's organisms trapped in the top of the ice, as we move down through that system, there's more and more biology. And so kind of in the lens of astrobiology, there's two big questions that this research is concerned about. And one is basically what determines the habitability of these ice-brine systems? What makes them, basically what limits how successful organisms can be in these environments, and what determines what places are going to be habitable and what determines what places won't be as habitable or uninhabitable. And then how do we detect these ice-brine systems on these other worlds using remote observation? So that is, until we can get there and actually take in situ sampling, how do we use spacecraft and other orbital mechanisms to basically take images of the surface and understand what's going on in the subsurface to determine where we should send missions or look for life? So kind of digging into this a bit more, some of the pros and cons of these ice-brine systems. So some of the good things that there is water availability. So because the brine is there and because it's salinating, it means that you can basically keep part of these systems in its liquid phase. So that's the brine pockets and the channels that we're seeing. And water is good for life, so that's a pro. Another thing is that it's a porous substrate. So the same way that in the ocean, there's a lot of organisms living in benthic communities at the bottom of the ocean because there's something for things to live in and be protected by. That bottom layer of sea ice, that porous region at the base here, is also a great place for microorganisms to kind of latch onto and be safe from grazers and other predators and things like that. Lastly, there's chemical and thermal gradients in this environment. So when you have this phase change between the solid ice and the ocean, kind of like moving through the different brines, and also as the salt is getting rejected out and moving in these porous regions, it sets up these gradients, and these thermal and chemical gradients are really great for life. The same kind of thing that we see in hydrothermal systems, where we have this phase system and this chemical gradient that's really helpful for things like metabolism. Some of the cons is also water availability. Because this system is essentially constantly freezing out, these organisms have to contend with the fact that they're going to have less and less water as this happens, although some of them have adapted things like EPS, which is basically a substance that can help resist that freezing. They can kind of modify their environment to deal with that. But then also, as these brines concentrate, things like your ionic composition is going to get really crazy, the pH, and also the water activity. The water activity is basically a measure of the availability of free water for organisms to use in microbial processes and stuff like that. So you can think about it like when these systems get very salty, it's the same thing why we put salt on food to preserve it. It like reduces bacterial growth, microbial growth, things like that. So once that water activity drops, it's harder for things to live. And so these are some of these key properties that we're interested in these ice-brine environments. So basically, when I think about this, I think this system kind of falls somewhere on this dartboard. So any kind of ice-brine system you have is going to have some quantity related to, its amount of habitability, whether that's something like Earth, that's going to fall like right in the middle. We know those things are habitable. Things can move around in time. Maybe ancient Mars was more habitable than it is now. And even just different regions on the same body could be at different locations and have different kind of habitability values. The surface of these icy worlds is probably really irradiated and hard to live on. But once you get down to the ocean or some of these brine pockets in the shell, it might be a lot better. So they might have these higher habitability values. So how do we determine what those are and where they fall kind of in this spectrum? The second thing is how do we relate what we see on the surface or using remote sensing data to the actual in situ habitability of these systems. So this is kind of just one example. This is kind of what we're think of when we think of these ice shells of these ice ocean worlds, where we have kind of all this diverse geology and geophysics happening on the surface, and that might be linked to all these subsurface processes. We might have fractures and plumes, or convective overturn or melting happening at depth within the ice shell. And those might be linked to these surface expressions. And we want to know how we can link what we see on the surface, which is what we have kind of on the right image here. This is just a picture of Europa's surface, to what's going on and what regions at depth are going to be habitable. So when you send this mission, do you want to go to the reddest area on the surface or the most broken and fractured area on the surface? Things like that. And so that's kind of the big key here, is to try and link what we have on the surface to what's going on in the interior and figuring out the best way to do that. So coming back to this idea, I think about this dartboard as having these scores around the edge, and basically, each score is going to be related to that interior habitability. But if we don't have a way to link up those systems, we're basically flying blind. So we can't relate what's on the surface to the habitability of that interior region that we're actually interested in. So a big goal is kind of connecting what we see on the surface in that ice to how habitable those like briny reservoirs are down at depth, where the ice maybe originated and formed. So we have a really great end member in sea ice on Earth. So at about 34 parts per thousand in a sodium chloride rich system, we have a really good idea of how the salinity of these environments evolved throughout time. So this left image is basically the salinity profile of ice throughout the season. We have good theoretical predictions for basically how fast the ice freezes or how it evolves, and how much impurities it's going to entrain in the ice. We also have a good idea of what kind of organisms live in the ice and where they're distributed. This image on the right is basically showing the bacterial distribution within sea ice. And you can see there's a really high load right near the base, even higher that's actually in the underlying water column. But the big question is, does this hold for other worlds that might have Ice-Brine systems that are both compositionally different or have even similar compositions but different concentrations than we have? So Mars might be rich in perchlorates or sulfates or things like that. We might have magnesium sulfate systems or sodium carbonate rich systems on these ice ocean worlds, or even the more complex kind of brines that we're talking about at the farthest reaches of the solar system that might be rich in hydrocarbons or ammonia or something like that. So that's kind of one of the motivations for going to these lakes in British Columbia. So just to get oriented, you guys are probably more familiar with this region than most talks that I give. But basically, these lake systems live right in between the Coast Ranges and the Rocky Mountains in British Columbia. So it's like, what, 5.5, 6 hour drive from here. What's really cool about these lakes is there's some really diverse geology up there. So basically what happens is they're closed basin lakes, and groundwater and surface water flow basically leaches out salts and minerals from the rocks and collects in these closed basin systems. And so we have these lakes with these wildly diverse compositions and chemistries. So you can get basically completely fresh lakes all the way to hypersaturated lakes where salts are actually just crashing out and precipitating on the bottom. And there's also a bunch of different chemistries. There's magnesium sulfate dominated lakes and sodium sulfate dominated lakes and carbonate dominated lakes. So basically whatever solar system brine you're interested in and you want to know how that Ice-Brine system kind of evolves, you can probably find a pretty good analog lake system up there to kind of represent whatever brine you're interested in. And so this is kind of an image of one of these lakes. A lot of them have this really interesting spotted pattern where you get these like sub-brine pools. So basically what's happening there is you have these ridges in between that are actually the sediments, and these brine pools kind of have these big salt bowls that get so saturated that the salt crashes out and basically forms these low spots that we think basically keeps precipitating and keeps sinking. And so you end up with this very like spotted texture. This is just some more aerial shots of some of the lakes that we go to. So you can really see these spotted textures here in all these different lakes. Sometimes they're very shallow and kind of, you can actually walk on these bridges, and sometimes they're completely underneath the water, but they all have these kind of very characteristic textures. Just to kind of call back the images from this like Mars lacustrine environment that might be magnesium sulfate rich, calcium sulfate rich. It looks even very similar to that kind of structurally as well. So it's probably a really good analog for that system. These are just some more images of these lakes. I'll just zoom through. These are basically, it gets saturated enough that these are actually just like efflorescent salts that are kind of precipitating on the edge here. And here's just kind of a view of what they kind of look like in winter. So they're not huge lakes and they're not very deep, but they do have these really interesting chemistries. So kind of our big goal for going up here was we wanted to go and basically take a bunch of different ice cores and samples and get like a really good biogeochemical data set of what's happening in these ices, so we can basically use that to constrain models that are trying to simulate what's happening in these planetary ice-brine systems to see if we can kind of nail it and match them up. So there's some more images of the lakes and some of the sampling we're doing. So to get into the data, so some of the things that we're looking at is just the stratigraphy of these systems. You can see again on the right, these are pretty shallow lakes, all less than 50 centimeters. A lot of times they'll have an ice layer, a brine layer, and then actually like a precipitated salt layer at the base that overlays the sediments. These are some images of some of these ice cores, and you can see these brine pockets and channels within the ice here. The bottom images are basically some of these hydrated salts that have precipitated out at the base of these lakes. And then Basque Lake 2, which has this interesting brine pocket actually within the ice. Was a really cool find that we saw when we went up there, and we'll talk about that a bit more in a second. We went up and we took thermal profiles. So basically when we take the ice cores out, we get a vertical distribution of the temperature of the ice core, which will be helpful later when we're looking at some porosity data. 2019 was very cold, so basically I have like this monotonic increasing temperature, but the brines at the base here, which are in the solid markers, are still very cold. You'll have brines that are -5C or colder, which is pretty chilly, and they're pretty salty. We also have thermal properties of the air and the brine temperature. So we went and put some temperature sensors up, and we can basically track these diurnal variations in the surface or in the air and the brine temperature until the center here in this red box where you can see the brine really stabilizes, which is basically we start to freeze ice on the top, which insulates it from those air temperatures. We do think we see like supercooling in this system. So we think these brines actually supersaturate before they start to precipitate this base layer. So we can actually get below the eutectic point or the saturation temperature of these brines. They start to precipitate out these salts, and then they kind of bounce back up and really stabilize for the rest of the season, which is really interesting. And then we also looked at biological and chemical profiles. When we go up and we take our ice core, we do things like ion chromatography and ICP-MS to basically look at the ionic composition of these ices, which you can see here in the colored dots. And then again, the brine at the bottoms are going to be the filled squares. And then also looked at cell counts. So those are going to be the black asterisks. So a lot of them kind of have a similar C-shaped profile to what we saw, what happens in sea ice. And then biology is typically lower at the top, higher at the bottom, which we also kind of expected. Except for this Basque Lake 2 here, where we actually had this internal brine pocket, this layer in the ice, where we basically drilled through and basically hit brine and then pulled out all the brine and kept drilling, and there was more ice. So there's this really concentrated, both compositionally and biologically, like water pocket within the ice, which was really interesting. We can take the chemistry data that we have and the temperature data we have and use geochemical models to basically back out things like porosity, which is basically the liquid fraction within the ice, which is potentially very useful for basically understanding, you know, how much available water there is for organisms in these systems. So 2019 was colder, so you're going to have a lower porosity on the left-hand side and a bit higher on the right when it was a bit warmer out. So one of the lakes that we went to was basically a really warm day, and so none of the cores were working. Basically, we'd drill in and brine would just start to percolate up. So we kind of improvised and did these permeability measurements where you basically can then drill down a bit and basically measure how fast the brine percolates up and get a measure of basically how permeable the ice is. So we hadn't planned to do that, but we did it. And we basically got permeabilities in these ice depths that match pretty closely to within the bounds for sea ice. So that was just kind of one more test that we did. We just got a paper accepted kind of with all of this data. So if you're interested in that, that is where to find that. And then we're also working with a group from Illinois State Geological Survey and Northwestern. Mitchell Barkledge had came up with us a previous year to do some really cool drone imagery on this left here, but he actually specializes in subsurface imaging using seismic and electromagnetic induction. So we ended up bringing him back up in the winter to get these really cool electromagnetic induction conductivity maps. So basically him and Bailey would go and walk these really tiring grid paths through like 1.5 feet of snow with this like electromagnetic induction thing to basically get these really nice plots that basically show these high conductivity ridges associated with kind of the spaces in between these brine pools, and then low conductivity spots where you have these big salt masses. Here's just one more image, kind of overlaying both the drone imagery as well as these conductivity plots. And at Last Chance Lake here, you can really see like how much higher these ridges are compared to these like kind of salt bowls that are down at the bases. And so they basically can go through, and because they're running at different frequencies, they can get full conductivity plots at depth, which is really cool. This is just one transect that they took and kind of their backed out calculation, and they can do that for that whole 2D grid, and they can actually produce these really nice 3-dimensional maps of the conductivity structure of the subsurface. And they're working on writing up a paper right now, which should hopefully be coming out relatively soon. But that was some really cool data and could be really useful for basically getting at kind of this subsurface structure, but also potentially how flow is happening underneath these lakes, because you can track the conductivity and potentially relate that to brine motion and things like that, which is really interesting because the hydrology of these lakes isn't very well constrained. So we're going to hop to another topic a bit. Basically, how do we take what we've kind of learned from these terrestrial systems and then move them up to planetary systems? So now that we have this analog, what is the next step? How do we kind of use that to make predictions for what's going on in these different planetary systems. So kind of stepping back a second, and from a really basic physical point, these saltwater systems, these ice-brine systems, are relatively distinct from kind of a pure freshwater system. So when we freeze out freshwater in our freezer or something, you basically just have an ice phase. You don't have a brine phase. You don't have a salt phase. So really how that ice is going to behave is just purely conductively, and you're not going to have any brine or fluid transport throughout that system. Whereas when you start adding salt to the system and freezing it out and forming these pockets and channels, all of a sudden you can have heat and mass transport both by advection, convection, conduction, all that. And so basically these images are just a fresh ice cube and then a saltwater ice cube. And you see when you pour food coloring on the top, there's a lot of stuff going on in this saltwater system. And so that's kind of what we have to contend with when we want to simulate and model the evolution of these systems. And so this is really similar actually to what happens in magmatic systems on Earth, where once you start to cool down this system that has these different components and can solidify out at different temperatures, you basically get this two-phase system that's going to evolve chemically throughout time. But just in an upside down process, basically. So you turn it on its head, you start to solidify out ice, and then you concentrate that brine. And so this image on the right is basically just what happens in sea ice. This is a laboratory grown sea ice, but basically you have a pure fluid at the bottom, and then you have this porous region with all these brine channels and all this dynamic processes happening. And so a lot of the work that I've done, aside from the fieldwork stuff, is trying to actually model these systems. So basically what we're doing is we use this two-dimensional multi-phase reactive transport model that basically simulates how ice and brine mass and energy and momentum is basically evolving in these systems. So we track things like fluid transport through porous medium using Darcy flow. We've got advection and diffusion and latent heat based on how the energy of this system is evolving, and also track how the salt is moving throughout this system, both diffusively and advectively, and with the ice kind of salinating these systems. And so this is kind of an example of what these 2D models look like. So basically what's happening here is we just have a cold surface and then freezing from the top down. So this is basically like what happens in sea ice. And we can see these really nice brine channels form and the brines being advective down. And we have this kind of like salinity gradient where there's higher salinity at the top and a lower salinity as you get deeper in the ice. And so these brine channels look really close to what we actually see in the field. When we take these ice cores, you can see these, brine channels forming in these ice systems. This is basically just, the other one was basically salt. This is basically tracking the solid and liquid fraction of the system. So you can actually see these porous brine channels as this layer freezes out. And they move around quite a bit, which is actually really interesting. And then you can see this kind of two-phase layer, which would probably be where any kind of biology or something would be happy, is kind of thickening as this ice progressively thickens. And we can kind of zoom in and look at kind of the details of these interfaces. So this is basically looking at this kind of slushy interface at different depths. The left plots are basically porosity, so the liquid fraction of these systems. And we can see these brine channels forming and this layer thickening. We can look at the brine salinity in these systems, and we can also look at the salinity gradient in these systems. So basically where these gradients are the highest, which could be something, like we said before, that's really important for sustaining things like metabolism or something like that. Looking at these salinity gradients, again, this is something that we basically see in some unique structures underneath sea ice. So these are called brinicles, which is basically like when you freeze the ice out and you get these brine plumes, they can actually form these kind of porous ice structures. And we actually can simulate that in the models that we're running. And we can show that basically where these brine channels are coming out have these really high salinity gradients, which is something that can basically be linked to an idea that could these brine channels or something like these brinicles provide something like hydrothermal systems provide at a sediment interface, but for this ice interface, to basically have this kind of this battery, this high gradient system that could be taken advantage of by any life. And just kind of one more look at, I think, how we're doing essentially is matching up, what we see in our model environment compared to what we see in these laboratory environments. And these, very dendritic structures that we see both in the model and in reality kind of supports that we're at least getting the physics right in these models before we kind of benchmark them against some of the systems that we see in the field. So what's going on this slide is basically the goal is to eventually take this model and run it against all these data sets that we have in British Columbia to see if we can start matching it up, not just against kind of like sea ice, which in a lot of cases just slowly freezes from the top down and is in that sense a bit more of a simple system, but kind of taking something like these wacky air temperatures that we have up in British Columbia that are jumping all over from melting in the middle to -30 degrees C or something like that. And then fully simulating the bulk salinity of these systems and the evolving liquid fraction, the porosity of these systems, and then the bulk salinity profile of these systems, which would basically be like if you went and took an ice core, that's what we would expect there. So the main goal of this is to be able to do all of the thermal dynamics, the chemical and the structural dynamics. Right now, that's where we're at. Eventually, we want to be able to do some biological stuff as well. Things like cells getting entrained in the ice, growth and death models, nutrient transport, stuff like that.
So your model is all in normalized kind of.
Yes, yeah, sorry, right.
Does it actually?
This is dimensionless, but you can get back out the actual data. And in the next one, I'll show we can do it against real values. So one of the unknowns at these lakes is what's the concentration of the brine when it starts to freeze? Because they're very shallow and the composition and the concentration can vary with how much rainfall and things like that you have. We don't know exactly what the concentration is when we start. We know the composition because we went up and measured it. But what we can do is we can run it for different starting concentrations, which is what we're seeing on the left. So this is everything else is the same air temperature forcing, the same composition, just a different initial concentration. These bulk salinity plots on the right-hand side are basically simulating what's happening on the left for these two different initial concentrations. And then the yellow is basically the ice cores that we actually took in the field. So that would be like the actual measured salinity values that we saw when we were up there in the field. And then the dots would be if you basically took those ice cores from the videos that were happening on the left. So those would be like the simulated ice cores for those exact regions. And we can basically try and match it up as that goes through. And this would be basically from this Basque Lake 1 is where we took the data from. And we do a pretty decent job, but these are like extremely dynamic systems that have a lot of things going on. So do we perfectly do it with these? Right now, these are some pretty preliminary stuff, but we're going to sweep through more basically initial concentrations and see if there's any other things that need to be tweaked that might be unknown variables to match up. But the general shape of the profiles does a pretty good job, especially the 121 towards the end. I said we didn't have any biological components yet, but we can pull out some properties that are really relevant for the habitability metrics that we might be interested in, things like water activity. So this is one snapshot of one of our simulations where we actually reproduce this kind of internal brine layer that we saw in the ice system. And then we can take the temperature and the chemistry and the concentration of these environments and put them into a geochemical software package and basically pull out things like water activity, which is something that's really important for basically determining the habitability of environments. And what we see is that this internal brine layer is actually has the highest water activity out of any region in the system. And that really matches up well with what we actually saw in the field for the case where we had that internal brine layer, where even though it was very concentrated in that layer, it also had the highest cell count of basically any site that we went up to. So kind of the ultimate goal is that if we can do this really well for these systems on Earth and we vet these models, then we can start to directly apply them to ice ocean worlds with a bit more confidence than the current models that exist and start to predict not only the composition of these systems, but also things like potential habitability. So when we go back to that dartboard picture, we might have a bit better idea for where to select, where to look for these different systems. So right now, kind of moving forward with at least the model architecture, some of these things that have been proposed to exist in these planetary ice shells are things like sills, where you would basically have some kind of water intrusion and kind of like a lateral lens or a layer of liquid that could freeze out from the top and the bottom, or also basal fractures, which is something that we see happening on ice shelves on Earth and stuff like that. We also see a lot of fractures all over the surface of these planetary bodies, but that you could basically have freezing from the edge to center. So that's kind of some of the simulations that we're running now with these models. And so basically the one on the left is kind of simulating what you would see on the top, where if you had this water intrusion that was actually isolated from the underlying ocean, and you froze it from the top and the bottom, you would have some really unique, basically, distribution of the salt in these systems that could potentially kind of concentrate anything in this residual pocket in the middle. And then on the right side, these are basically fractures that are freezing from the edge to center. And you can see that we get these really unique kind of structural features, these kind of diagonal brine channels that show up both in the porosity profile and in the salt profile. But what's really interesting is these features actually match up really well with what we see in other two-phase systems like metal alloys and stuff. When you just solidify ingots or something like that for metallurgical processes, they get these same segregation patterns in metals. So these aren't any kind of numerical dispersion result. These are actually structures that we think would happen if you start to change the geometries and do different things with these features. So I'll just leave the conclusions up and say that we really like these lakes as kind of a really valuable ice ocean analog because they have all of these different compositions and concentrations and things like that. We think that it's a really good benchmark data set for models that are trying to simulate planetary ices that have these different compositions. And that once models can basically simulate all of the dynamics that's happening in these kind of more complex compositional systems, I think only then will it be kind of appropriate to scale them up to these different environments confidently. So yeah, that's all I have.
All right, I'm sure that Jacob would be happy to take questions. So any questions?
Yeah, really, can you go back to the slide where you showed like the first growth of the multi-component top layer? I believe in the first one.
This one?
Yeah, I think this one.
Let me go back and forward so it'll hopefully play.
Yeah, or just the one just after that, like the one that showed the porosity.
The porosity?
Yeah. So when you see that you have like the, what you see is that the double, like the two-phase layer is very thin at the beginning. It's been thicker with depth. Do you have a reason why? Is it like dynamic? Is it just kinetics?
Yeah, so basically in these systems, the top of that is basically going to be the eutectic temperature, and then the bottom is basically going to be the freezing point. And you can match that out pretty well. So in this paper that we had, we basically looked at the evolution of that thickness, and like it'll be just barely different because you'll have some brine convection and some downwelling, but it's almost exactly right on point with like the line of your eutectic. So if you just drew like a conductive profile from your like thermal coursing to the bottom, basically the top of that two-phase layer is just where everything freezes out.
Okay, so what you're seeing in the end is just like the change of the slope of the time of the temperature.
Yep, exactly.
In this simulation, like when you have the transition beyond the eutectic, do you take into account the change of volume of the hydrate?
No, so there's no volume change in these models.
And do you have any other hydrate properties like the thermal conductivity, or you just go to ice?
No, it just basically hits a solidus, and then will be just all the like thermal properties are just going to be basically for a pure ice system, nothing with the hydrates, but that sounds like a sea freeze problem.
Don,
There's a lake in eastern Washington called Hot Lake,
Yeah,
which is extremely hot in the summertime. So there's no convection, there's just a strong gradient in the density of salt. So do your lakes get hot in the summer?
that's a really good question. I don't know off the top of my head. I know they are a bit meromictic, like they don't mix that well. Like we've gone up and the people that I work with have taken brine samples from the top and the bottom of the lake and seen different kind of like water masses. They're pretty shallow. So like if you get any kind of wind, I think it can mix them pretty well. So like on a windy day, they'll start to like de-stratify sometimes. Whereas if you have ones, there's some that are like really forested and they don't get like the same wind that like, I don't know, if you guys, Last Chance Lake can get pretty windy sometimes when we've been up there. It
they're
gets-
all pretty shallow too, right?
Yeah,
So
yeah.
There's not a lot to mix.
But in some of those, the brine pools and some of them that don't get a lot of wind and are in the woods, they can remain like pretty stratified still.
Hot Lake, all shallow.
Oh yeah, how do you know how deep it is?
Never been there.
I think it's deeper than like the typical 1 meter.
Yeah,
that these are, and it's also very dense, right? It's a density stratification, which is partly responsible.
Apparently that's the secret to Hot Lake. It's a high density gradient.
Yeah,
Is it always cold at the bottom? Like, does it stay pretty cool at the base or?
no, it's
Oh,
hot.
it's hot.
It's
Hot at the bottom.
Yeah,
Okay, gotcha.
it's a so-called solar lake.
Yeah.
Some people have studied to contain heat.
How about the speed of crystallization of the water? Did you consider that? And what effect did it have on porosity?
On the porosity. So you're talking about just like the rate of ice formation on
That's
how
correct.
porous
Speed
the
of-
ice.
I don't know what speed you're using, but did you consider changes in the speed of crystallization so that the crystal can get larger?
Yeah, so unfortunately we don't like simulate individual crystals. Like it's basically just a continuum model. So we basically just have the porosity is just going to be basically calculated by how salty your system is essentially, and you just have like some freezing point depression. But I definitely agree that, right, it's going to have an impact, right? If you have slower freezing, you should be able to grow bigger crystals, presumably. I would think. Does that make sense?
Other questions, Sebastian?
With the cell count increasing with depth in the ice cores, sounds like you think that they're living in there or not just dormant, like making it through the winter. And so related to that, do you know that? And I wonder if they just try to escape the freezing ice down into the brine. And so related to that, I was wondering if you had cell counts in the brine that's under the ice to see if those are just the unfortunate ones that were able to escape completely. Frozen to the ice. They actually like to be in the ice to some degree.
Yeah. So I haven't done any kind of live dead testing to see like if they're viable or if they're living. My intuition is that they will be. One reason is that like they still will autofluoresce if you hit them with like a UV light. I don't know if like that's a feature of dead cells or like if they can still do that or not. I'm very much not a biologist, but I think it would be similar to sea ice where they are just kind of trying to follow that permeable space. I think one of the tricky things is that with all the freezing and melting cycling, like that could vary quite a bit throughout the season here. So I don't know, but like because this brine pocket has such a high density, I was talking to somebody last week at this conference that asked a very similar question, like, why is there such a high density in this like brine pocket in the middle? Like, did they all just end up getting concentrated there, or did they like get put there and then like explode and like grow a bunch, right? Like, are they actively reproducing there? And like, maybe they didn't start with a high concentration there, but it was liquid and it's close to the surface and they're competing against nobody. So they just like flourished in that environment. So I think like doing a live dead test of like those cells would be really, really good to like figure out who's living where and how well they're doing.
Rory?
Yeah, I was wondering if you try yet to sort of extrapolate your modeling of like brine tunnels on Europa, say, or something like that, and think about what is the volume, total volume across the whole surface of these habitats potentially for like.
Ooh.
Sort of look into that yet?
I haven't. That's a good question. So you're talking about like volume or surface area of kind of like all of the porous region,
Yeah,
essentially.
yeah. So just what could be like the volume of the habitats across these?
Yeah.
From the model?
No, I don't have numbers for that, but like it'd be very easy to extract to say like, okay, if we assume the shell is this big and this porous region is this thick, like this is how much habitable space we would have. Yeah, that's a great idea. I think, yeah, good way to extrapolate it out.
But related to that, you know, what you're dealing with here is centimeters. So somehow or another, you have to scale this up to tens of kilometers or whatever, and pressure dependencies, different gravity, and so on. So how are you going to move in that direction?
Yeah. So we've done a bit of that scaling. Like if you're in this conductive region where you're actively freezing out ice, kind of like what Baptiste had mentioned, this layer is basically set by your thermal profile. So wherever that eutectic is, you should have brine stable anywhere in the shell that is above this eutectic temperature for whatever composition you have. The problem is if these shells get thick enough, they could potentially start to like solid state convect in these layers. And then it's kind of like all bets are off for these models, because all of a sudden, like we're just modeling fluid flow through a porous system. But this is kind of saying like, well, eventually on a geologic time scale, if this ice shell gets thick enough, then your entire system starts to like viscously move. And that's like, all of a sudden you're trying to spin a lot of plates at one time. So I don't think there's no models yet that integrate both of those. I know there's some folks in Germany that are trying to use some of the parameterizations from our models to link those up with like full solid state convection. So people do solid state convection, and then we do this mushy layer stuff at the base of the ice shell, but there isn't any connection between those two yet. So I think people are starting to try and make them work together, which I'll be very interested to see like what those kick out.
Any more questions? Yep.
I'm curious if you thought to incorporate or looked at incorporation like convection of increased protein for EPS and the maintenance of the pore space while the ice freezes out.
Yeah, that is a great question. That's hopefully our next step to like try and do, I think like talking to people in the biological community, like EPS and these antifreeze things are like the are thing to be like, that's what you should do next kind of thing. So I think like one of the big questions I have is like, how do we treat cells in this system? Are they along for the ride, and do they get entrained the same way salts get entrained? Or like they can get there and then all of a sudden they're like, this is better, let's move somewhere else. So you have to have this kind of like mobility of the cells, but then you also have to have like their ability to modify their environment and like produce these EPS proteins and things like that. So I think the hardest part, like we'll be able to put it in the model. We just need to put it into equations essentially, right? Like if there's equations to describe it, we can put it in the model, but it's coming up with like those equations that I think is the hurdle. So if you have any ideas, I'm happy to talk.
Other questions? Are there questions from the unseen audience on Zoom? Doesn't sound like it. Well, if there are no more questions, let's thank Jacob once again for.
Yeah, thank you for having me.
Yeah, that's great. So I think you can kill Zoom people.
That's right. I'm pulling the plug on that.
6 people? There might have been more earlier.
Yeah.